In this video, we are going to take a look at the fundamental theorem of calculus. Specifically, we are going to look at part 1 of that. We will make a couple quick notes that we may remember from our calculus days. So when we look at a Riemann integral from a to b of a function, this is equal to the negative of the Riemann integral from b to a. And also, if you look at the Riemann integral from a to a of f, that will be equal to 0. All right, so fundamental theorem of calculus, part 1. This says, let f be be integrable on the closed interval from a to b. For each x in a to b, we are going to define f of x to be equal to this integral from a to x, f of t dt. After we do that, or if we do that, then we are able to say that f is uniformly continuous at c in that closed interval. Furthermore, if f is continuous then f is differentiable at c. And not only that, but we can also say that the derivative of big F at c is little f, right? Where that little f is that function that we are integrating. All right, so let's prove this. So we have a number of things that we're going to need to prove. So let's see what we can do. So what do we know? Since little f is integrable on that closed interval from a to b, we know it is bounded. On that interval. So we know that. So what does that mean if we say it is bounded? Right? So that is there exists some number b greater than 0 such that the absolute value of the function values is less than or equal to that value of b for every single choice of x in that closed interval from a to b. So we know that to be true. So to see that f is uniformly continuous, on that closed interval a to b. So to see this, we let epsilon greater than 0 be given. So let epsilon greater than 0 be given if x1 and x2 are both elements of that closed interval a to b with x1 less than x2 and the distance between x1 and x2 being less than epsilon over b, then what do we have? Well, then we're going to have the absolute value of f of x1 minus f of x2. That absolute value is equal to the absolute value of the integral from a to x1 f of t dt minus the integral from a to x2 f of t dt. Which here we can flip those limits of integration and change that negation. Right, and so, or we could change this negative and flip those limits of integration. When we take the absolute value, then the negatives will go away. But at any rate, we end up with the absolute value of the integral from x1 to x2 f of t dt. And this should be less than or equal to what we would get if we took away those absolute values. Right, so if we just drop the absolute values, then the value of that integral should be less than or equal to what we would get if we, or rather than dropped it, if we move those absolute values inside. All right, so any function values that were below the y-axis, we are really flipping those up above the y-axis, and so we end up with looking at all positive areas that we are adding together, and not these negative values, these negative areas under the curve. But we know the absolute value of f of t, that is bounded by b, so this is less than or equal to the integral from x1 to x2 of b dt. But b dt, or the value of this integral, is equal to b times x2 minus x1, which should be less than b times epsilon over b. And so we get our uniform continuity. So we get big F is uniformly continuous on AB. All right, so now let's continue this, and now suppose that F is continuous at C. In that closed interval. Then, given any epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of little f of t minus little f of c. That absolute value is less than epsilon whenever the difference between x and c, so whenever t is in that closed interval, and the difference between t and c is less than delta. Right. So since it's continuous, then we know that to be true. And we can say that since f of c is constant, we can write f of c f of c equals 1 over x minus c, the integral from c to x, f of c dt. For x not equal to c. Then for any x in that closed interval AB with 0 less than x minus c less than delta, we have the absolute value of big F of x minus big F of c over x minus c minus f of c, which is equal to 1 over x minus c times an integral from 0 to x, f of t dt, minus integral from 0 to c, f of t dt, minus f of c. And so, similar to what we did before, we can write this as 1 over x minus c, an integral from c to x, I said zeros, those should have been a's. So, integral from c to x, f of t dt, minus 1 over x minus c, f of integral from c to x, f of c dt. So here we've rewritten f of c in this way, because prior this was only being multiplied by that portion. So we've rewritten our f of c using that observation from above. And so that allows us to factor out the absolute value of 1 over x minus c. I guess we can put this together as a single piece. Minus f of c dt. And so this should be less than or equal to that absolute value of 1 over x minus c. And then here for this other stuff, we could drop the absolute value sign. So we can write it as an integral from c to x f of t minus f of c dt. And so if we drop the absolute value sign from just this piece, this should change kind of appropriately, or that part is all right. And then this should be less than the absolute value of 1 over x minus c. We have identified that this mess is less than epsilon. And so that's what we're seeing right there. I said drop the absolute value sign. That's not quite right. I meant bring the absolute value sign in, just as we did before. Made exactly the same verbal mistake. And so we get that this is less than the absolute value of 1 over x minus c epsilon, and then the other stuff, when you take that x minus c, is what you are multiplying it by. And so that's going to cancel, and so this is epsilon. Therefore, f prime of c, big F prime of c, is equal to the limit x approaches c of f of x minus f of c over x minus c. This value is equal to little f at c. And we are done. Whew! That's a big theorem. Part 1 of the fundamental theorem of calculus. We can now believe we have that it's true, and so when we've used it, we've been using it fairly. All right, we will talk to you later.